This telescope is going to change astronomy forever. Not slowly either. It's capable of rewriting our understanding of the universe. As of right now, we have a general idea of our known universe, since we understand that there are billions of galaxies and billions upon billions of planets orbiting distant stars. Here's the thing. The universe is said to be constantly growing, but we don't know the full story. Let me expand. No pun intended. The universe is made of something known as dark energy, an unknown force that we can't fully understand. We don't know why it exists, and we don't know if our laws of physics fully explain it. Yet. Because this is where this new telescope comes in. It's called the Nancy Grace Roman Space Telescope, NASA's next great observatory. This telescope is not designed to look deeper than ever, but instead, it's designed to look wider than ever. Imagine taking a photo of space. Hubble captures a tiny detailed slice. Roman will capture an area 100 times larger, with the exact same sharpness. Instead of studying just one galaxy, Roman will scan millions. Even planets drifting alone in the darkness between stars will be visible. But the most ambitious goal is not just to view the planets and take cool space photos, although that is a perk. Roman will map the universe on a massive scale, tracking how galaxies cluster, seeing how light bends through space, and how the structure of the cosmos evolved over billions of years. By doing that, it may finally reveal how dark energy behaves and will answer some of the biggest unanswered questions in science. What is the universe actually made of, and where is it going? To answer these questions, it will use gravity itself as a tool, watching how it bends light over great distances, which will allow us to detect planets we could never see directly. It will be as if we just unlocked a new section of our universe, with new planets, hidden black holes, and exploding stars across billions of light years. The amount of information the Roman Space Telescope is capable of collecting is unmatched. Some scientists believe that this mission could produce the largest dataset in the history of astronomy, and allowing us to finally see the universe in a completely different way. So what exactly is Roman Space Telescope? It's a successor to missions like Hubble. However, it's not intended to replace all telescopes, as it's a beneficial addition to the James Webb. Roman was not intended to zoom in on singular parts of our universe. Its goal is to discover the universe as a bigger picture. Now remember that. Originally, Roman was a mission called WFIRST, the Wide Field Infrared Survey Telescope. Over time, the mission evolved. Its design grew more advanced, and in 2020, it was officially renamed after Nancy Grace Roman, recognizing her role in shaping modern space astronomy. The telescope has a mirror that's about 2.4 meters wide, the same size as Hubble's, meaning it will have the same clarity on all the images as Hubble, except Roman will have a 100 times view, surveying huge portions of the sky in a fraction of the time. This raises a problem though: storage. Roman is expected to output approximately 1.4 terabytes in one day, 500 times more data than Hubble, and over its 5-year mission, upwards of 30 petabytes of data. So, with this data problem, scientists cannot download it normally. They have to use cloud-based systems, since they want to map the universe and basically create a high-resolution atlas of the cosmos. To do that, Roman carries two main instruments. The first, and most important, is the Wide Field instrument. This is the heart of the telescope, a massive, ultra-sensitive camera with a resolution of about 300 megapixels. It captures both visible and near-infrared light, allowing it to see through dust and observe objects billions of light years away. With this instrument alone, Roman will observe hundreds of millions of galaxies over the course of its mission. The second instrument is smaller, but definitely not insignificant. It's called the coronagraph. Its job is to block out starlight. Stars produce such a bright light, basically preventing views of the faint light produced from nearby planets. By removing that light, the coronagraph can reveal objects that would otherwise be hidden, being planets orbiting other stars. So what's the actual plan for this telescope? After launch, Roman won't orbit Earth like Hubble does. Instead, it'll travel nearly 1 million miles away to a region in space called the Sun-Earth L2 point. This location is perfect for space telescopes as it allows for a clear, unobstructed view of this universe right behind the Earth. The position also allows for a cool and stable environment for the instruments, perfect for creating the end goal of a detailed map of the cosmos, and allowing scientists to analyze patterns, trends, and structures of our universe. Let's take a look at how the Space Telescope actually works. It works in its own unique way, different from other telescopes. Light from distant galaxies enters the telescope and hits its primary mirror, but instead of simply bouncing onto a camera, Roman uses a carefully engineered series of mirrors. Each reflection reshapes and focuses the incoming light, correcting distortions while preserving the detail. This design also allows the telescope to have sharp focus throughout a large area of the sky. This design is so important since normally telescopes really struggle with this. The wider you try to look, the more distorted your image becomes at the edges. However, Roman solves this. Its optics are designed to keep the entire field in crisp, high resolution, which is exactly what makes future massive panoramic images possible. But capturing light isn't just enough, because a huge part of the universe is actually just completely invisible to our eyes. Let me elaborate. Cosmic dust fills galaxies, being microscopic particles from stars made of rocky, sandy, and icy material. And it's a problem, since it blocks visible light, hiding stars and planets. Trying to observe those regions with a normal camera, you wouldn't see anything. So Roman doesn't primarily rely on visible light alone. It looks in infrared. Since infrared light has longer wavelengths, it means it can pass through the space dust clouds, and because the universe is expanding, light from distant galaxies gets stretched as it travels. What started as visible light arrives at Earth as infrared. So by observing infrared, Roman is essentially looking back through the past. The feature that truly makes Roman special is the wide field imaging. Most telescopes are built like microscopes. They look at one object in incredible detail. And of course, for space discoveries, that's super useful, but not very effective at visualizing the entire universe as a big picture, which, remember, is the final goal. You're only seeing the tiny pieces of the universe at a time. So instead of focusing on one object, Roman uses a wide field image to view millions of stars and thousands of galaxies in one frame. Imagine you're looking at a distant star. Behind the distant star is another shining star. You can't see it directly because the light is too faint, but then something passes in front of it. A planet, or a star, or something of similar caliber. And as it moves, its gravity bends the light behind it. And for a split second, that same distant star appears significantly brighter. This phenomenon is called gravitational microlensing, and Roman uses it very effectively to find quote-unquote hidden planets. Before Roman, missions like Kepler revolutionized exoplanet discovery. However, just like most tech, it had its limitations. It could only detect planets that happened to pass directly in front of their stars. What does this mean exactly? Well, if the orbit didn't line up just right, Kepler would miss the planet completely, and Kepler focused on a relatively small patch of the sky. Roman one-ups this because instead of waiting for the perfect alignment, it watches millions of stars all at once. By continuously monitoring dense regions of the galaxy, it can capture gravitational microlensing events as they happen. And because microlensing doesn't depend on starlight, Roman can detect planets in places Kepler never could. But the real question is, what kind of planets are planned to be scouted? There are 3 planets of mention that Roman will specialize in. Rogue planets, planets that don't orbit any star at all, and are now drifting through interstellar space. Cold, distant planets, planets that exist far out of their solar systems, beyond the equivalent of Jupiter and Saturn, places where temperatures are low and orbits take decades or centuries. Low mass planets. Because of how sensitive microlensing is, Roman may detect planets smaller than Earth. Worlds that are incredibly difficult to find with other methods. Although the real breakthrough is not singular planets, but instead populations of planets, answering questions about how common are our solar systems, or how many planets are out there without any stars. Because, remember, the whole goal is to look at the bigger picture. This takes me to the next idea, dark energy. If you zoom way out, and I mean way out, you see something strange. The universe isn't just a random scattering of matter. Galaxies are grouped together. They form vast structures that stretch across space, and between those structures, there's something that makes up the most of the universe. Something we can't see. As talked about earlier, it's called dark energy. And it's something that scientists don't really understand. It doesn't emit light, it doesn't absorb light. It's something that makes no sense, but we know it exists. For a long time, scientists assumed that the expansion of the universe should be slowing down, which makes sense, but that's simply not true. When we actually measured it, we found the opposite. The expansion is accelerating. Galaxies aren't just moving away from each other, they're moving away faster and faster. Something is pushing them apart, but it's weird because the force simply comes from empty space, meaning the very fabric of the universe is expanding due to the dark energy. And the telescope plays into this because Roman takes large-scale observations, which is needed to understand dark energy, which all in all reveals the mystery of the expansion of the universe. And when you combine all of these aspects into one big analysis, you make history. This isn't just another telescope. It's a tool for understanding the universe in a bigger picture. Comment your opinion on this new telescope, and I hope you enjoyed the video. If you did, consider subscribing.